Section 6.5 is the central limit theorem, and this was kind of what the last section was building up to. The central limit theorem is a big deal. It tells us that for a population with any distribution, the distribution of the sample means approaches a normal distribution as the sample size increases. The reason that normality is good is because we can use our calculator and the normal CDF in order to find probabilities and work with this and solve problems. The procedures in this section forms the foundation for estimating population parameters and hypothesis testing. That's what the last half of this course is going to be about. With any theorem, you're given conditions that must be satisfied, so we're going to have to check these given conditions to see if they're valid. If these given conditions are valid, then the conclusions are going to hold true. The given conditions here is that the random variable x has a distribution which may or may not be normal with a mean and a standard deviation. You don't have to make sure that that random variable comes from a normal distribution. It doesn't have to. The second condition is that a simple random samples of all size n are selected from the population. So given any distribution and you select a random sample of size n, the samples are selected so that all possible samples of the same size have the same chance of being selected. If that happens, then the distribution sample of the mean will, as the sample size increases, approach the normal distribution, no matter what the original distribution shape is. Typically, if your sample size is greater than 30, then you're okay. You can assume normality. The mean of the sample means is the population mean. The mean of the sample means is the population mean. And then the standard deviation of all sample means is the standard deviation divided by the square root of n. And do you remember me mentioning that in the previous section? I said I was laying the foundation for this. As long as you have a sample of size n, then the mean for the sample distribution will be the same as the population, but our standard deviation is going to change. Some practical rules that are commonly used. For samples of size n larger than 30, the distribution of the sample means can be approximated reasonably well by a normal distribution. The approximation becomes closer to a normal distribution as the sample size gets larger. The larger the sample, the more normal the distribution. However, if your original data comes from a normal distribution and you know already it's a normal distribution, you don't have to have 30. You can get by with fewer than 30 samples. Well, that's what number 2 says. If the original population is normally distributed, then for any sample size n, the sample means will be normally distributed, not just the values for your sample size is larger than 30. Here's the notation for the mean of the sample means. Mu sub x bar is going to be the mean, and the sigma sub x bar is going to be the standard deviation of the sample mean. That's sigma divided by the square root of n. This is also referred to as the standard error for the means. So our new mean and distribution for the sampling distribution looks like this. Now y'all said that a picture's worth 1,000 words, and I want to show you some pictures here. If our original population were normally distributed, and we take a sample of size 1, we're going to see a normal distribution. If we increase our sample size to 10, we still end up with a normal distribution. Each dot here represents 11 observations. Here's a normal distribution. As our sample size increases, notice the mean of the original appears to be the same no matter what our sample size is. The mean appears to be the same, but the standard deviation is getting smaller as our sample size increases from 1 to 10 to 50. You can tell that by our distribution shrinking in. Here's a distribution that's uniform starting out with our sample size equal to 1. Can y'all see those little dots there? If we increase our sample size to 10, this is roughly a normal distribution, but it's a lot rougher than it was over here when our original data values were normally distributed. But by the time we get to our sample size being 50, this clearly takes on a normal shape. This population is U-shaped. It's almost the inverse of what the normal distribution is. It's like flipping the normal distribution upside down. And we have a U-shaped distribution if our sample size is 1. If we increase the sample size to 10, we see that kind of flip around. And if we increase our sample size to 50, this is clearly a normal distribution. As our sample size gets larger and larger, then the distribution becomes more normal. An important point: as the sample size increases, the sampling distribution of a sample mean approaches a normal distribution. Here's an example problem that I like to use that I think makes this concept of sampling distributions make sense. So suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500 pounds. Assuming a worst case scenario in which the passengers are all male, what are the chances that the elevator is overloaded? We're told here also that males have a mean weight of 182.9 with a standard deviation of 40.8 pounds. That elevator holds 16 people or 2,500 pounds, which gives us an average of, let's go to our calculator. If I take 2,500 and I divide that by 16, we get 156.25. So on part A here, it says find the probability that one randomly selected male has a weight greater than 156.25. We expect it to be more than 50%. Because the average weight of a male is 182.9 and this is less than that. Question is how much more? So here we're looking at an individual male that has a normal distribution of 182.9 and a standard deviation of 40.8. So we draw our normal distribution. Always start with a picture. What number goes in the middle? 182.9. And we're looking for the probability that we have a male with a weight of 156.25 or greater. Will that number go to the left or the right of 182.9? Left. Let's put them over here, 156.25. And do we want to shade to the left or to the right? Right. So we know we're looking at a weight or probability more than 50%. So we're going to do normal CDF. What is our left bound going to be? Our right bound? I'm going to use 10,000 now because 1,000 feels too small to me. The mean, 182.9. The standard deviation. Alright, so let's do this on our calculators right fast. So the probability of a random male having a weight greater than 156.25 is 0.743. Part B here says find the probability that a sample of 16 males, worst case scenario, have a mean weight that exceeds 156.25, which puts the total weight at 2,500 pounds. If their weight's going to exceed 156.25, then we would exceed the weight requirement for the elevator. But this is not the same distribution. We're now looking at a sample of size 16. The mean distribution is still the same, 182.9, but what is the standard deviation going to be? Standard deviation there is going to be the 40.8 divided by the square root of 16, and this is going to be 10.2. So that means we're going to be shrinking this distribution in a lot. For part B, we draw our picture. What number goes in the middle? And we're still looking for the 156.25. Only our standard deviation is much smaller. And we still want to shade to the right. Please understand, these pictures are not drawn to scale. So on our calculator, we're going to do normal CDF. The only thing that's going to change here on our normal distribution is the standard deviation. The 40.8 becomes 10.2. That's 99.5 or 0.6. So either the manufacturer needs to make stronger elevators or we need to lower the passenger requirement if we're really worried about the elevators crashing to the ground. I have never had to use this, but that doesn't mean that I won't have to use it in the future. If you have a finite population, it says when sampling without replacement, and that's why we like sampling with. If you're sampling without replacement though, and the sample size is lowercase n, and that's greater than 5% of the finite population, meaning we can't assume independence, then we will adjust the standard deviation for the sampling means by multiplying it by a finite population corrector, and that's given by this formula. We only have to use that if our sample size is more than 5% of our population and we're sampling without replacement.